All right, so let's continue with chapter 13, probability rules. So we're going to look at a little something different in this one, but continuing on with what we were talking about. So let's introduce the idea of a contingency table. So a contingency table is just a table that displays two categorical variables. And so you see one here. And so this is summarizing a survey of high school students. It asks if they were a boy or a girl, and then ask which of these was most important to them. So either getting good grades, being popular, or being good in sports. And so you can see the breakdown. So 227 boys, so that's the boys row. We had 247 that said they wanted good grades, and then 117 of those were boys, et cetera, and then 478 total students were in this survey. So if we want to ask what's the probability, so a randomly chosen student, what's the probability we choose a girl? So we see there are 251 girls in this survey, and then out of 478, so we'll just write 251 over 478. And then, of course, we can get the decimal, but we won't do that here. So then probability that a randomly chosen student is a girl and wants to be popular. So we're going to find where those two intersect, and that would be 91. So we have 91 of those out of 478. And then last, we have probability that a randomly chosen student wants to be good at sports. And so we go to the sports column. We have 90 who want to be good at sports, and that's boys and girls out of the 478. All right, so those are very easy to do. And you notice all of these denominators are 478 because we're just looking at out of the whole student body, what's the probability that we get whatever this is that we're looking for. So how many of those, or how many of those that want to play sports, whatever it is. But what if we know something about the person? So what if we know the chosen person is a girl? So you randomly pick a student. You were informed that the student is a girl. Now, what's the probability that the girl's goal is sports? So the way we write this, well, first of all, let's say we know this part. So we know the person was a girl. So now we're only going to look at the girl row. So we're not worried about the girl, or we're not worried about the boy row. We're not worried about the total row. We're not really worried about the columns individually. We know the person is a girl. Now, of these, so we have 251 girls. How many of those girls want to be good at sports? So we would actually write this as sports. So the probability of sports, and then we're going to draw a vertical line. And the vertical line is a conditional. So whatever comes after this is the part that we know. So we know that the person is a girl. So given this, you can read this like given. So what's the probability the randomly chosen person wants to be good at sports, given the person is a girl? So we know this part. And then given what we know, what's the probability of the other thing? So if we want to find probability of sports given girl, we're looking at the girl row. So we have 251 girls. That gives us our bottom number. And then in this row, how many of these want to be good at sports? That would be 30. So the probability of sports given girl is 30 over 251. All right, how about we try a different one? Find the probability of selecting a boy given the goal is grades. So we know the person wants good grades. So that will come second. That comes after the conditional part. And now what's the probability the person is a boy? So how many of these students want good grades? That would be 247. So we're only in the grades column. So let's only look in the grades column because that is what we know. So we have 247 that want good grades. How many of those are boys? 117. All right. So with these two examples in mind, let's see if we can come up with a formula. And it'd be helpful. Let's see if we can keep this keep the table in there as well. So let's say probability, just generically speaking, of B given A. So we know that, whatever that is, that's the part that we know. So we'll write this probability B given A. Again, A is what we know. Now, given that A is true, what's the probability that B is also true? So if it helps, we can draw a Venn diagram. This may or may not help. It'll probably help some people, maybe not others. So we have A and B, we have the overlap there. Now, given that we are in A, so we know that we are living in this A circle. Now, given that we are in the A circle, that will be our bottom number. So whatever that probability is, given that we are in that A circle, now what is the probability we are also in that B circle? So that would be our top number. That's going to be the probability of A and B, or B and A, if you like. So here's the part that we're given. We know that this part is true. Now what's the probability we are also in B? So a lot of people want to write probability of B over the probability of A, but that doesn't hold, because probability B, you could also be over here. If you're over here, you are not in A, but we know in this case that we are in A. So it would be kind of like coming up here and saying, if we said boy given grades, so 247 would be our bottom number. We can't say that 227 is our top number, because that includes these boys over here that don't want to have good grades, at least not top priority. We can't include those in if we're only in this column. So we're only in this column, so we can only look at the boys in this column. Same thing with the sports given girl. If we're in the girl row and we're looking at sports, we can't include this 60 up here, because that's not part of the girl row. So we're only looking at the girl row. We're only looking at the grades column. We're only looking at the A circle. All right. So make sure that you understand this formula, and it's not always as explicit as find the probability of this given that. So it's not always saying a given. A lot of times these will kind of look like an and problem, but it doesn't have the word and in it. And so I'm not sure if we have an example of that, but it's not always as explicit as just saying this given that, but it's the idea. So when you see problems, pay attention to if there is something that you know for sure is true. All right. And then given that that is true, what's the probability of the other thing? All right. So back to the relationship in sports example. If you see a student athlete, what is the probability this athlete is in a relationship? So we have, obviously you don't see the word given here, but an if-then statement is going to be a conditional. So this will be the part that we know. So we know that the person is an athlete or they play sports. So we will write the probability of a relationship given sports. And so that will be the probability of both over whatever the part is that is after the vertical line, or the given part, the if part in this case. So 11% are in both, 25% are in sports. And then I'll let you divide that out and we get what we get. Okay, so general multiplication rules. So we talked about the multiplication rule we gave last time said if A and B are independent, the probability of A and B equals probability of A times probability of B. So remember, and means multiply. So if we look at the probability of both, they're independent. We have the probability of A times the probability of B. So what if they're not independent? And again, independent means if A and B are independent, if A happening does not change the probability of B happening. So what if they're not independent? So whether they are independent or not, we can write the probability of A equals the probability of A given B. Or we could write the probability of A and B equals the probability of A times the probability of B given A, or obviously you can switch those around, so we can say the probability of B times the probability of A given B. So either of those things are true, and typically you see these things with kind of sequential events like we talked about last time, and they may or may not be independent. If there's just because they're sequential doesn't mean independence. The ones that we saw in the last chapter, we were assuming independence, and they were independent. Talking about the red light coming to it each day, the whatever it is on Monday does not affect what it's going to be on Tuesday or Wednesday or Thursday. So those are independent events, but dependent events, a lot of times you'll see this where you have a box of shirts and they're different sizes, and you pull shirts out and you have 10 small and 5 medium and 8 larges, and you pull one out and it's a small. Now you just have 9 smalls. And so it changes all the probabilities. So let's look at an example. And I don't know that it's not super important to memorize this formula because you can kind of use it without knowing the formula, but to get the idea. So basically, this one means if A happens, then what's the probability that B is going to happen given that A already happened? So they're sequential events, and then the second event probability depends on the first event probability, but it's not super complex. So let's look at this example. So a salesperson has a 75% success rate in closing deals during their initial client meetings. If the first meeting results in a successful deal, the probability of success goes to 88%. So if the first one is successful, the probability the next one is successful goes up to 88%. So what's the probability the salesperson closes in the first two meetings? So probability, let's say we'll just write closes first and closes second. These are not independent because depending on what happens in the first changes the probability of what happens in the second. So if the first one is successful, then the probability the next one is successful goes up. So this would be the probability the first one is successful times the probability the second one is successful given the first one is successful. And all this is, and you could probably do this without writing formulas because you're going to see all we're going to do, the probability the first one is successful is 0.75. And then the probability the second one is successful given the first one is successful is 88. So all we're doing is multiplying those two. So when you see these and you realize this is kind of an and problem, just multiply the two numbers and it doesn't get too really any more complicated than that. And this comes out to 0.66. And so that's all we're really doing. We're just doing an and. If it was independent, it would just be 0.75 times 0.75, I guess. But it does give you an if clause here. So that tells you that the second meeting is conditional on the first meeting. So, but either way, we're just multiplying those two together. And that's how we do that. All right. If you have any questions, let me know.